Hello, everyone. I'm Riccardo Calaon. I'm a third-year PhD candidate at the AVS lab at CU Boulder. And today I'm presenting this work, which is the result of a collaboration between myself, Cody Allard, and my advisor, Dr. Hans-Peter Schaub. The title of this paper is Continuous Center of Mass Estimation for a Gimbaled Ion Thruster-Equipped Spacecraft. Before getting to the paper itself, I wanted to provide a brief um, overview and motivation to this paper. Here we are showing two of many missions that fit the same profile that I want to describe here. One is the NASA Dawn mission launched in 2007. The other is the NASA Psyche mission launched in 2023, or that is hoping to launch by the end of 2023. What these two missions have in common is that they both feature electric propulsion. Specifically, they both features a gimbal thruster that can adjust the thrust vector with respect to the hub. Now, why that is done? Primarily, it is done because as the center of mass of the spacecraft evolves during the mission, it is necessary to adjust the thrust direction to account for that. That is just the primary reason, but as a recent contribution from myself and my two co-authors has shown, this was a paper published or presented during the GNC conference in Breckenridge earlier this year, is that if we have a gimbal thruster, it is possible to articulate and orient the direction of the thrust vector with respect to the center of mass to perform momentum dumping. Now, what we are showing here is the result of a simulation run for seven days, where on the left, we see the reaction wheels speeds over time when no momentum dumping is being performed. Therefore, when the thrust vector is fired through the center of mass, we see that the reaction wheel speed blow up pretty significantly. Whereas on the right, we are showing a case where the thruster is performing constant momentum dumping on the system, so offsetting the thruster with respect to the center of mass allows us to maintain the wheel speeds within bounds that we feel comfortable with. So to summarize the introduction, the center of mass location can change over time, primarily due to mass depletion, but also due to the movement of articulating appendages such as solar arrays or the thruster itself. And whether it is to perform momentum dumping or to simply avoid momentum building up on the system due to the thruster, it is necessary to estimate the location of the center of mass as it changes over time. Now, the question that we are trying to answer in this paper is how or can we exploit the thrust and the torque that it produces to inform us about the center of mass location? Now, I'll move on to describe the simulation that we are carrying out here. The simulation involves a bunch of parts that are treated as rigid bodies, the first one being the spacecraft hub, which is actuated by 4 reaction wheels in a pyramid configuration. There are 2 rotating solar arrays that are attached to the spacecraft by means of a single degree of freedom hinge, and a dual hinged platform that is attached to the spacecraft by means of a 2 degree of freedom hinge. So this platform can perform tip and tilt rotations with respect to the hub. This is particularly important because the solar electric propulsion thruster is mounted on such platform. Therefore, moving the platform effectively moves the thrust vector with respect to the hub. The spacecraft is on an interplanetary trajectory, and solar radiation pressure is acting on the system. This is the control law that is acting on the spacecraft. It has the form of a nonlinear PID-like controller, where the first 3 terms are effectively the proportional, integral, and derivative parts. All the other terms are gyroscopic terms that are added to the control law in order to ensure asymptotic stability. Now, the integral feedback term is particularly important in this application because it zeroes constant unmodeled external torques acting on the system. Now, when the location of the center of mass is not known exactly and the thruster is firing at an offset with respect to the center of mass, the torque that produces is exactly an integral, a constant unmodeled external torque. So the importance, the presence of the integral feedback term is essential to ensure that we can effectively track the reference frame that we need. Now, the equations of motion of the system as a whole are derived with the assumption that the platform and the solar arrays, so the rotating appendages, reach their own steady state faster than the rest of the system, which is in general a fair assumption. And within that assumption, we can treat the whole spacecraft as a rigid body with a constant inertia with respect to the center of mass, which in general it isn't when there are moving appendages. So these are the equations of motion that govern the whole system. If we consider that the reference frame is the frame that we are trying to achieve in order to align the thruster with the inertial pointing, so this reference frame cannot be moving. As a result of that, the reference that we are tracking is constant, and therefore the problem boils down to a regulator problem, which also allows us to further simplify the control torque acting on the system. Effectively, the control torque with these assumptions does take the shape of a PID controller, and it only depends on the integral, proportional, and derivative terms. Now, if we analyze what happens to the system once the hub also reaches steady state, well, by definition, the proportional and the derivative terms drop to zero because the relative attitude and relative angular rates with respect to the reference, they all drop to negligible values. So if we take a look at the control law, we can observe that the only term that survives at steady state is the integral feedback term in the control law. So that is the only force that the reaction wheels need to be delivering constantly to the system in order to ensure that pointing. Another interesting factor that can be observed is that when this final steady state is reached, there is no further dependence from the inertia of the system, which is good, because if there are errors in how we are modeling the inertia of the system as a whole, these errors don't show up at steady state in the control torque. So now that we have described our system, I want to spend a few words describing how center of mass is typically performed during missions. Typically, this estimation is carried out thanks to accelerometers that are mounted on the spacecraft. And first of all, it is possible to observe from the first equation, which is the relative acceleration theorem, that under the assumption that the center of mass doesn't change location, at least over short periods of time, we can already lose a term. And therefore, it is possible to express the acceleration experienced by the accelerometers as a linear mapping that depends on the location of the center of mass. However, there are a series of problems here, which are first of all, this model works with a spacecraft that is not subject to a constant force, which is not our case. We have a thruster that is operating over extended periods of time. So when this is the case, to estimate the center of mass, we also need to be able to factor in the mass of the system into the problem, which also needs to be estimated. But most importantly, the dependence between the acceleration that is being measured and the location of the center of mass relies on non-zero angular rates and accelerations of the hub. Now, this is a problem for when the spacecraft needs to fundamentally stay still and not rotate in space to ensure the pointing of the thruster. What does this mean? It means that nominally, center of mass estimation, in order to be performed successfully, requires calibration maneuvers. That is, the spacecraft needs to be spun around in space such that this dependence between the measured acceleration and the center of mass becomes observable. That is a problem because we do not want to break the nominal course of operations. So here's why this novel approach comes into place. So if we look again at the spacecraft equations of motion, we can once again show that some terms drop out because once the system has reached steady state, the angular rates of the hub drop to zero. It is therefore possible to observe that there is a correlation between the control torque, which is being delivered to the system and is a result of flight software, and the torque that the thruster is producing on the system. Now, if we explore that correlation even further, we can formulate it according to this linear law, which also depends on some new points that we are introducing in the system, which are point T, which is the point through which the thrust vector is being applied, and the location of point T is assumed to be known. And then point B, which is the origin of the body frame, which is also known at all times. So effectively, the quantity that we are trying to measure here is the location of the center of mass with respect to point B. With respect to point B. And the first assumption made here is that the SRP torque is not acting on the system. Now, looking at this linear model from a static configuration, so when the thrust vector is not changing over time, it is possible to notice that this problem is not observable. Now, because the matrix that defines our linear relation has rank 2, and because the system, the variable that we are observing does not have dynamics, so does not change over time, this problem is not observable. However, as the paper that I talked about earlier in this presentation has shown, we do not want the thrust vector to remain fixed with respect to the hub. But rather, we want the platform to move over time in order for the thrust vector to help dump the momentum that is being added to the system. So taking this into consideration, we can look at the generalized observability matrix for the system and observe that whenever multiple observations are made from linearly independent thruster configurations, this problem does in fact become observable. So as long as we keep moving the platform, we can gain linearly independent observations that can help triangulate the location of the center of mass. Moving to the estimation algorithm, this is a recursive least square algorithm, weighted least square algorithm that effectively coincides with the correction step of a Kalman filter. There is no prediction because the assumption is that the center of mass is not changing over time, so its dynamics are 0. The only difference here is that we introduce a convergence error, which is an estimate of how well we have converged to the reference frame, and updates are only made whenever this convergence error drops below a certain threshold. Beyond that, all the equations here that tells us how to update our knowledge of the center of mass and the covariance are effectively the prediction step of a regular Kalman filter. So nothing new under the sun as far as this goes. Now, how does this algorithm perform? We start by showing the results of a very short simulation. The simulation is only run for 3 hours without SRP acting on the system. The initial covariance is of 5 centimeters. So our initial guess of the center of mass is within 5 centimeters along each component from the real location of the center of mass. The platform is being moved every hour. And we can observe that in less than 2 hours, we get a pretty good estimate of the location of the center of mass. Now, this makes sense because if a if an individual observation is not does not make the problem fully observable, 2 linearly independent observations, which is what we get after 2 hours, are in theory sufficient to triangulate the location of the center of mass. So this is what these first estimation results show, that after only 2 platform movements, we can go from an uncertainty of 5 centimeters to an uncertainty that is fractions of a millimeter. So we have 2 orders of magnitude improvement in our knowledge of the center of mass. Moving over to the dynamics of the system, if we look at the attitude plots, we can see that every hour the attitude of the spacecraft is being changed. This is because as the platform is being articulated, we also need to move the whole spacecraft to ensure that inertial pointing of the thrust is being achieved. Looking at the reaction wheel plots, we can see that some reaction wheels are increasing their speeds in the first part, in the first hour. This is when the thruster is not being fired through the center of mass. However, when the first correction maneuver kicks in after an hour, we can see that the platform is reoriented in a configuration that immediately dumps that momentum that was being built up. So what we are showing here is that as we are learning where the center of mass is, we are improving our pointing ability and also ensuring that momentum is being dumped at all times. But so we want to push this a step further and see how does this behave when we add uncertainty to the system. So These results show the estimation during a simulation of 3 days with solar radiation pressure acting on the system. Now, the initial conditions are the same. There's an uncertainty of 5 centimeters on each center of mass component. And what we see is that we are not estimating the center of mass as well as we were before. Even when a coherent measurement noise is added to the system in a way that makes the post-fit residuals make sense, we can observe that there is a bias that stabilizes to a constant value on all 3 components of the estimated center of mass location. So obviously, we asked ourselves why this is the case. However, if we look at the attitude plots and at the general dynamics of the system, we can see that the system is still reaching a stable configuration after a certain amount of time. If we look at the reaction wheels, we can see that their speeds increase and decrease subsequently over the initial early stages of the simulation. However, they also stabilize around a certain value without momentum being accumulated on the system. Same thing goes for the platform angles, which initially they move around as we are articulating the platform, but then they settle onto a constant level. So it looks like the system is still stable, despite the fact that the estimate that we get on the center of mass is biased. So effectively, what is happening here is something that we did not initially understand, but the combined action of the control law that is regulating the platform with our estimation of the center of mass does not, in fact, stabilize onto the center of mass when external perturbances are being added to the system. However, the system is settling onto a configuration that ensures that no momentum is being added to the system, which means that once we reach steady state, the thruster is fired along a direction such that the thruster torque is counterbalancing the torque that SRP is producing on the system. As a result of that, the point whose coordinates we're estimating are not the coordinates of the center of mass, however, but instead the coordinates of this point, which ensures equilibrium of the entire system. As a result, and here I'm concluding this presentation, the algorithm is successful at estimating the center of mass location in the absence of external perturbations that affect the torque measurements. When such perturbations exist, the combined action of the estimation algorithm and the control law have the system settle about a point, which is the equilibrium point for the whole system. This point whose coordinates we're estimating is not, in general, the center of mass. However, we may not care. In fact, we needed to estimate the center of mass to know where to fire the thruster, but it seems that the direction along which we want to fire the thruster is not the center of mass, but it's the direction of this magical equilibrium point that we are ultimately estimating. And also, this stability property of the system might become useful when we will eventually add uncertainties in how we are modeling the thrust vector. So we might not know exactly where the thruster is firing or if it's firing at the desired with a desired magnitude. So all these factors would add to the unmodeled torques acting on the system, but as this simulation has shown, it is possible to still achieve stability and keep momentum from building up on the spacecraft. Now, thank you all for listening to this presentation. If you want to reach out and have any questions, here is how you can reach out to me, and I wish you all a pleasant day.